This isn't necessarily every little thing from chapter 19, but these were definitely the main topics. So enzyme classifications, the 6 classifications, definitely know those. Factors that affect enzymatic activity. I don't know if I have a problem specifically for that on here. But we talked through how temperature, pH, and substrate concentration are the 3 major things that affect enzymatic activity and how they do that. Enzyme regulation and the types of inhibition. That was a big one. That was a biggie. So I got some problems for that. And then vitamins and minerals. All right. So let's just jump in. Try not to use your notes. Try not to use your lecture slides. Try to pull from your memory. How many of the enzyme classes do we remember? There's 6. And what do they catalyze? What kinds of reactions?
I remember hydrolase.
Okay. What do they do? Anybody remember?
They break up the reactant by adding water.
Yeah.
And the product, 2 things.
So they catalyze hydrolysis reactions.
Lyase.
Mm-hmm.
Now what it does.
The addition, whoops. Or elimination of functional groups. And no hydrolysis, without hydrolysis.
There's ligase.
Mm-hmm. What do they do?
I'm like Maggie.
Does this one involve CO2 or phosphates?
Ligases, there's an example. They bring together compounds. So they catalyze the bonding of 2 substrates. So for example, your synthetases, all right? Anything that's bonding 2 substrates. So like the addition of a phosphate group to, well, that would be actually probably be more like a kinase, but anytime you're bringing together 2 substrates and you're binding those together. So when we bring together acetyl-CoA and oxaloacetate in citric acid cycle, that's a ligase.
Catalase.
What was that, Cameron?
Catalase.
Adalase? It's not one of the main classes.
Isomerase.
Aldolase is a type of enzyme. We talked about that recently. Why did we talk about aldolase recently? Oh, glycolysis. That's an enzyme in glycolysis that splits your fructose 1,6-bisphosphate in 2. Yes, but what was somebody just said, one of the other main classes?
Isomerase.
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 And it catalyzes the rearrangement of atoms in the substrate. Nothing's added or removed, we just rearrange. have some
Transferase.
isomerases in glycolysis. What was that, Claire?
Transferase.
Yep. Okay. These catalyze the transfer of functional groups. So this is where you have your kinases, they phosphorylate. Transaminases. Transaminases we talked about in chapter 25 with amino acid catabolism. We have the transaminase reaction where you switch the double bonded oxygen and amino group. Okay, that leaves one.
Oxidoreductase.
Yep. Catalyze oxidation reduction reactions. I would say we've spent most of our time with hydrolases and oxidoreductases. Just because metabolism is a lot of redox reactions and hydrolysis reactions, okay? All of these enzymes are important, but we especially spend a lot of time with, or should like your dehydrogenases, your proteases. Those are the classes 1 and 3. Okay. That's that problem. Any questions on that? Enzyme inhibition. Let's talk about the various modes of enzyme inhibition and explain or make statements about how they're different. So, anybody remember a type of enzymatic inhibition? How do we regulate enzymes? We don't always want them turned on, going at their maximum catalytic rate. Sometimes we want them slowed down. Sometimes we want them turned off. So how do we regulate?
There's uncompetitive inhibition.
Yes, there is reversible. I'll go ahead and say competitive and uncompetitive. And there's reversible. Uncompetitive inhibition. So how are these two different?
Uncompetitive, that's whenever the enzyme binds to either the substrate or the active site.
In competitive, it can bind to the active site. It competes with the true substrate for the active site. So you got two molecules, they can both bind the active site. Whichever one's present in greater amount will be the one that binds to the active site more often. Okay, so that's the competition. Both can bind the active site. Which one's going to bind depends on the concentration. The one that's present in a or concentrated, more highly concentrated amount will compete out the spot for the active site. So here, the inhibitor can bind the active site. Okay. What about uncompetitive inhibition? How is it different?
Doesn't the inhibitor, like, it doesn't necessarily fit the active site, but it can like prevent the other substrate trying to get into the active site, right?
Here, yeah, very close, Claire. The inhibitor, it doesn't bind to the active site, but it can bind to the enzyme substrate complex. You guys know what I mean when I say enzyme substrate complex? What does that mean? I'm going to say ES complex. So we use this little notation it's on one of your slides in your enzymes lecture. So if you have this, for example, if you have this enzyme and you have your substrate bound in here, okay, then the inhibitor, we'll just do it in green, okay, it can come in and bind the enzyme substrate complex so that the substrate cannot leave. And then it's just stuck and the enzyme's inhibited because it can't release the substrate, the catalytic activity is slowed down or inhibited or slowed down in this way. Okay, so it binds the enzyme substrate complex. It can bind to my picture actually may not be the best because it looks like the inhibitor is binding the active site. The picture that's probably a little more accurate is the one right here, okay? So in uncompetitive, the inhibitor doesn't actually bind the active site. My picture, it looks like it does. But it just keeps the substrate from getting out, okay? So just, that's how they're different. So that might not be the most accurate picture, but what other modes of enzyme inhibition do we have?
Feedback.
Feedback, yep. So I encourage all you guys to be writing this with us, okay? It's gonna help you if you're writing these things down, taking notes, writing things down definitely helps our brains remember them, okay? I know you get note cards, but there's no way you can fit all this stuff onto all your note cards. All right, feedback inhibition here, the end product of a pathway. So like, for example, glycolysis, the citric acid cycle, we've talked about multiple pathways. One of the final products comes back and it inhibits. At what point in the pathway do we inhibit an enzyme?
Is it back to the very beginning?
Yeah, we cut off one of those initial first steps. In glycolysis, we can inhibit both steps 1 and 3, which are early on in the pathway, so we're not wasting a lot of resources making all the other intermediates that we don't need. So an end product inhibits an enzyme early in the pathway. Okay. So the way that looks, if we have substrate number 1, and this would be enzyme 1 to product number 1 to substrate number 2, enzyme 2 and enzyme 3, what it might look like is this final product right here comes back and inhibits the first enzyme so that we cut off the pathway if we have enough of that product. Irreversible inhibition. All right, what is this?
Is this when it stops, it doesn't start again?
Yeah, the inhibitor binds and it doesn't come back off. Permanently, okay? And any other kinds? Still got a few more.
They're negative allosteric.
So So we've got allosteric, we've got negative and positive. All right, so negative. A negative regulator, what happens here?
I might be wrong because I think I'm mixing it up with the positive one, but is it when the inhibitor is binds somewhere else on the enzyme and it once it's like binded, it prevents something from getting into the active site?
Right, so a negative regulator, okay, binds enzyme at a location different from the active site. And what this causes is a conformational change in the protein, in the enzyme. And that change structurally affects the protein and affects the active site so that the substrate can no longer bind the active site. This leads to a conformational rendering an active site that is no longer available. Okay. Now, a positive regulator is going to also bind the enzyme at a location different from the active site, but it's just that the conformational change that happens after that opens up the active site. Okay, so a positive regulator so it both do the same thing. The part I'm going to highlight, they both bind enzyme. Whoops, I thought I was unhighlighted. Bind the enzyme at a location different from the active site and cause a conformational change, but they just have different effects on the active site. One affects it in a negative way, one affects it in a positive way. And this is not even everything. We still have a few modes we haven't talked about. What other kinds of enzymatic regulation do we have?
Is there genetic control? Or
Genetic control, and then there's one more. Maggie's throwing a party. Genetic control and
The zymogen?
yes, which zymogen was an example of covalent modification. Okay, so the two other kinds, I'll just write them down here. Okay. Covalent modification. All right, so in genetic control, it's just that enzymes are regulated by their synthesis. The body only makes them when we need them at certain stages of life. Okay. Covalent modification, the enzymes are already synthesized and they're ready to go. It's just like they're asleep. They're in a zymogen, an inactive form. And then there's all different kinds of modifications we can that can give us the active form. We could cleave off a particular portion of the primary sequence. We could phosphorylate certain amino acids to turn it on to the active form so that it's ready to go. So one way we could covalently modify is cleave of the primary sequence. And that cleavage will turn the enzyme on, give us the active form. Or two, we could phosphorylate serine, threonine, tyrosine residues. Okay, and both of these are forms of covalent modification. So that's a lot. That's why I put a star on this main topic, because this plus the classifications of enzymes was huge. All right. This and one more slide and we're done with chapter 19. So real quick, let's look at this problem. We actually worked this as an example. So you probably have notes on this from your lecture slides, but we have not worked this. I want to know what you guys think this kind is. In oxidative phosphorylation, cyanide can block ATP synthesis by binding to cytochrome C oxidase at a site other than its active site, essentially shutting down the electron transport chain. What kind of inhibition is this? So oxidative phosphorylation, we know what that is. Cyanide, which is poison to our human bodies for understandable reasons, can block ATP synthesis by binding to cytochrome C oxidase at a site other than its active site. And it can essentially shut down electron transport chain. What kind of inhibition is this? What do you guys think? So what kinds could we, this does not sound like covalent modification or genetic control. It says nothing about the fact that the enzyme is asleep and then it's cleaved or it's phosphorylated. Nothing about the enzyme is synthesized at certain stages of life. We always need to be making ATP. So whatever enzyme is involved here, or cytochrome C oxidase is the enzyme, we always have it. So it's not genetic control or covalent modification. So could it be allosteric control, feedback inhibition? Well, it would, to be feedback inhibition, cyanide would have to be a product of the pathway. Our bodies don't make cyanide. So it's not feedback inhibition.
Is it negative allosteric?
Okay, I want to hear from some other people too. Is it negative allosteric? What Maggie thinks. Binds the enzyme at a location different from the active site, causes a conformational change. So it does say here that it binds the enzyme at a site other than its active site and essentially shuts down the enzyme. What do y'all think?
I was thinking negative too.
Yeah, so without any other additional information, I think this is the best choice because it doesn't say that it binds the enzyme substrate complex. Okay, so we can't necessarily say that it's uncompetitive inhibition. It doesn't say, it says it does not bind the active site, so it's definitely not competitive inhibition or irreversible inhibition. So allosteric, control would be the best bet here. Okay. All right. Last question on chapter 19. Why are vitamins and minerals important? What's the main overall purpose of vitamins and minerals?
Isn't it to get nutrients that our body doesn't make ourselves?
Yes, yes, but why do we need those nutrients? What do they do for us?
They help our body perform functions that, like, I know vitamin A turns into beta carotene, right? Or is that vitamin C? Forgot. One of those vitamins turns into beta carotene, and that like helps you with your eyesight and night vision. And I don't know how to correctly say it. I know what they do.
They help our body in many ways. There's many like physiological effects, but they're all mainly acting through a similar way. For all these helpful things to then happen. Okay, remember what we said was that vitamins are mainly used as cofactors or coenzymes. Okay, they aid enzymatic action so that these things can be, they act as antioxidants. That was another thing. And again, down here, these are minerals are cofactors, right? So their main primary function in the body. The reason we need to eat our vegetables, obtain vitamins and minerals is one, because our body does not synthesize these, as Claire mentioned. But the way they perform, they help our body is they act as cofactors, coenzymes, and antioxidants. Okay. So that's chapter 19. All right, I know we've been doing this for a long time now, but we have one chapter left. So I would like everybody to participate as much as possible. I know we're all exhausted at this point in the summer and we're ready for all this to be over. But give me the best you got for the next 30 minutes. Let's get through chapter 21. And then we will have reviewed, 3/4 of this course, which hopefully this is helpful. I mean, I'm doing this for you guys. So I hope that y'all are getting all that you can out of this. I know it's a lot of writing down information or trying to think through slides, but writing things down helps you remember it. So, and y'all are gonna need to know it for tomorrow. Okay, biochemical energy, the main topics here. We talked about delta G and why delta G is important, how we determine if a reaction is favorable or unfavorable from delta G simply by looking at the sign. So somebody remind me, what does negative delta G mean?
Question.
Yeah, Cameron.
Will this chart be back on the final exam like it was on exam 4?
Like to fill it out? No.
Yes.
No, it's not on the exam. But it's right here because this information and just how everything flows together is one of the big picture charts that I really liked, so that you see how all these different pathways we've looked at flow together. All right, so delta G, what does a negative delta G mean?
Isn't that like good?
Yeah, that's good. That means the reaction is
Favorable?
negative delta G. Okay, so what that means is the opposite, positive delta G, the reaction is not favorable or unfavorable. So we call negative delta G exergonic, positive delta G endergonic. Then we talked about the strategies of metabolism. Oh, by the way, any reaction in one direction with a negative delta G, in the opposite direction, it has a positive delta G. Same value, same number, just different sign. So reactions are always favorable in one direction, unfavorable in the other. Strategy of metabolism. We said pathways, the fact that things happen in pathways, meaning, for example, the product of glycolysis, pyruvate. Well, it just so happens that pyruvate is the reactant for the conversion to acetyl-CoA. So acetyl-CoA is the product of that, but acetyl-CoA is the reactant for the citric acid cycle. So they all feed into each other in this way, okay, so that nothing is wasted. So that's one strategy. And then coupled reactions, the fact that we can take exergonic reactions and use those to drive endergonic reactions. Okay, we're going to look at an example of that. And then we talked about how coenzymes, the fact that these cycle back and forth between their reduced and oxidized forms so that we can run these redox reactions. Okay, we always have a steady supply of oxidizing and reducing agents to power and aid metabolism. Okay. All right, so that was NAD plus and FAD to NADH and FADH2. All right, then we hit the citric acid cycle, electron transport, and oxidative phosphorylation. Those are the main topics. So let's talk about coupled reactions. So explain how coupled reactions work from a metabolic standpoint. What do you guys think? How do coupled reactions work? You could explain this to me many different ways.
An endergonic reaction couples with the exergonic reaction, so it can have energy to have a product.
Okay, so we can say an endergonic runs spontaneously or is coupled to an exergonic. And what's important is that the energy required to run this reaction is smaller than the energy released from the exergonic reaction. The exergonic reaction has to release more energy than is needed to run the endergonic reaction. Okay. You could tell me that exergonic reactions are like downhill reactions. Okay, so a larger downhill reaction can be paired to a smaller uphill reaction. Okay, remember that if we talked about the energy charts and we used that example. Okay, I actually have an example of two reactions right here. What if we coupled these reactions? I want you to tell me what the final overall reaction would be. Calculate the delta G, and then tell me, is this favorable? Would the exergonic reaction here be able to power the endergonic reaction? Overall, would the coupled reaction be favorable or unfavorable? So remember, if it's got a positive delta G, this is unfavorable. It's got a negative delta G, this is favorable. So what would the overall reaction be?
Is it unfavorable?
Maggie, you're right. The overall reaction would be unfavorable. Anybody calculate the delta G?
1.7.
A positive 1.7. Because it's a positive value, it's unfavorable.
Are we gonna be doing like the same math that we did this past exam? Is that gonna be included on the final? Like, will we need to bring a calculator?
Yeah, bring a calculator to the final. Okay, so your overall reaction should be, you can cross out C from both sides and B from both sides. So A plus E makes D plus F. But this reaction is not favorable, okay? The exergonic reaction is too small. You'd have to pick a different exergonic reaction. One that released more energy. Okay, so that's coupled reactions. Citric acid cycle. Which steps yield energy or high energy molecules? Which steps are the energy yielding steps or produce high energy molecules. You guys remember? So we have 8 steps here. We have acetyl-CoA and oxaloacetate. And these come together. They give us citrate. And then we isomerize the isocitrate. So this would be step 1. Step 2. Step 3, we get alpha ketoglutarate. Anybody remember? I didn't ask you guys to remember all the intermediates. Alpha ketoglutarate, succinyl-CoA, succinate, fumarate, malate. Which steps, this was what we drew out in lecture, which steps produce high energy molecules?
Doesn't step 5?
Definitely step 5, because we make ATP there, okay? So step 5 was one of them. What other steps? What, Abby?
Was it step 3?
Step 3, anytime you make a reduced coenzyme, that's a high energy molecule. Those feed directly into electron transport, okay? Where we have to be continuously releasing energy to pump protons. So anytime you make an NADH, we said that was a high energy molecule. So step 3 was one. What other steps?
Step 4?
Step 3, step 4, step 5,
Step 8?
step 8, and step 6, okay? So steps 3, 4, 5, 6, and 8. So almost every step in this pathway, except for steps 1, 2, and 7, give us something useful. This is why the citric acid cycle is so important. So we'll just write over here, steps 3, 4, 5, 6, and 8. All produce either a reduced coenzyme or ATP. I'm not going to finish this. Okay, but basically you can look at that figure that we wrote out in lecture. Those are the steps that are important. So know the overall products of the citric acid cycle. What all do we make from the citric acid cycle? You guys remember what the net products were?
Was it 2 NADH?
Close, 3 NADH.
3. One FADH?
ADH2,
2 ATP?
1 ATP.
1.
Step 5, that's it. We only get ATP from step 5.
H2O.
Close, we get 2 CO2. Okay, those were the final products. These all go directly to where? So that's actually the next question. How is the citric acid cycle linked to the electron transport chain?
Doesn't the electron transport chain need, no, I'm thinking of something else. I was gonna say it needs oxygen. I was thinking about,
It does need oxygen, but that's not how these two are linked.
I know the reduced coenzymes are used in the electron transport chain.
Mm-hmm. So the reduced coenzymes produced by the citric acid cycle, what do they go do?
Do they get oxidized?
Yes, they are oxidized in the first step of the electron transport chain. So in their oxidation, they release electrons that travel through the electron transport chain. So they feed electrons to the electron transport chain. Okay, which leads us to the electron transport chain. So I have like 3 questions left. So walk through the electron transport, or walk through electron transport layer by layer. Discuss how the movement of electrons produces a proton gradient and how that gradient is used to make ATP. Okay, so I'll get you guys started. NADH, FADH2, we said the first step here is that they're going to be oxidized back to their original forms, NAD plus, FAD. So this is oxidation. And in doing so, they're going to pass electrons to complexes 1 and 2. Okay, what happens next?
And then does it pass through the COQ? I can't remember what that is.
Coenzyme Q.
Is it? Oh no, I'm thinking of iron. Which one is iron?
Cytochrome C.
Okay.
So coenzyme Q, we didn't get into the specifics of coenzyme Q, but it goes from being reduced, or sorry, oxidized. When it picks up the electrons, it's reduced. And then it just cycles back. And as it cycles back to its oxidized form, it passes the electrons to complex 3. Remember, the gain of electrons is reduction. The giving away of electrons or losing electrons is oxidation, oil rig, if that helps you. Okay, what happens from here?
The oxidized becomes reduced in the cytochrome C and passes on.
Yep, and what atom was it specifically?
Iron.
So we go from iron. Anybody remember the charge rotation?
2 or 3.
So it starts out as iron plus 3. When it picks up those electrons, it becomes iron plus 2, which makes sense that the charge goes down. And then as it gives electrons back to complex 4, it regenerates the iron plus 3, which can just go back and keep picking up more electrons and keep the cycle running. Okay, what's the last step? Last step, anybody remember?
Does it have something to do with pumping hydrogens through?
We're about to get to that.
Okay.
So hydrogens are being pumped as we go through this. But where do these electrons land?
Does it form oxygen or?
It goes to oxygen.
Oh, okay.
So specifically, an oxygen atom is half of an oxygen molecule, but we always write it as an oxygen molecule in a chemical reaction. So the electrons go to oxygen, and we make water. Okay, how, so that's the movement of electrons. How does this pump hydrogens? How does it produce a proton gradient? Hydrogen ions.
Isn't there more hydrogen ions on outside the matrix or the electron transport chain?
Yeah, so by the way, which side is which? We haven't even labeled our membrane.
The matrix is the bottom part.
Yep. This is the intermembrane space up top. So how does the movement of electrons produce how do we get a proton gradient out of this?
It's got to go through active transport, I think. Right?
Yes, which requires what? What does active transport require?
Energy.
Energy. Where does the energy come from?
Oh, is it the oxidation?
It's the redox reactions. Literally the movement of electrons as things become reduced and then oxidized, reduced and oxidized. Energy is released with every single step. It is the movement of electrons that releases energy. So as these things are oxidized, they release energy. Okay. Now complex 2 does not pump protons, but it still does release energy, which is harnessed to pump protons for other. So as this coenzyme Q and cytochrome C, this all releases energy. Okay, every redox reaction in this chain is energetically favorable. Negative delta G. These are all reactions, redox reactions. Every single one of these is used to release energy, and that released energy is used by the complex to pump hydrogen atoms okay, remember complex 2 does not pump hydrogen atoms across into the intermembrane space. And you end up with a concentration imbalance. Okay. So the energy comes from the redox reactions, from the cycling of oxidized to reduced forms. Oxidation reactions are generally always favorable. They release energy. Okay, so complexes 1, 3, and 4 pump the hydrogen ions. And then how is this used to make ATP? This requires, ATP requires a lot of energy. When I say gradient, what I really mean is that you have a high concentration of hydrogen ions on this side, and we have a very low concentration in comparison of hydrogen ions on this side. So there's a, and then all these ions are charged. So there's an electrostatic potential as well. You have a high amount of charge on one side, a low amount of charge on the other side. So how is this used to make ATP? this gradient?
Then the hydrogens are pushed through the, right, they go through the ATP. Is that the synthase?
ATP synthase. So these hydrogen ions are channeled back through here. Are they moving against their gradient or down their gradient when they're moving this way?
Down the gradient.
Down the gradient. Things that move down their gradient, this is very energetically favorable, okay? Moving against the gradient requires energy. Moving down the gradient releases lots of energy, especially when you have a huge separation of concentration, a huge separation of charge. This is associated with a lot of potential energy, okay? And moving down the gradient is what causes protein complex to turn, the energy released from that. And we take ADP plus the phosphate, and from that, on the beta subunit, we get ATP. Okay. All right, that's electron transport, oxidative phosphorylation. Last two questions here. Where do these take place? Where in the body? Where does citric acid cycle, electron transport, ATP production, where does this happen?
Is it in the mitochondrial matrix?
Yes. All right. And then which form of the essential coenzymes is the oxidized form and which is reduced? So we're talking about NAD and FAD. What is the oxidized form? What's the reduced form?
Is FAD oxidized and then FADH reduced?
Yep, FADH2. What about the other essential coenzyme?
NAD plus is oxidized.
Mm-hmm.
And then NADH plus H plus would be the reduced form.
Perfect. Okay, that's all I had for you guys. I hope this helps. I know these types of things are, you know, not the most riveting things in the world, but I hope you feel like you've covered, we've covered a lot of topics. Again, I'm not going to say we've covered every little thing to get you ready for the exam, but we've covered a lot of the majors, okay? So, any questions before we take a break? I mean, I am going to have an office hour today. Yesterday, no one really showed up, so I kind of just jumped off and got some other things done. So probably today, if nobody shows up within the first 20 minutes or so, I'm going to treat it the same way. But by all means, I want to be there to help. If you've got questions on your Flipgrid video or, you know, what to do or how that's supposed to go. But nobody shows up after 20 minutes or so, I'm probably just going to put my head down and get some things done. Okay, guys, you're almost there. One more day.
Is that at 2:30? you said?
2:30. All right, if there's no questions, then y'all take a break. And remember tomorrow when you show up, you don't have anything due except for your Flipgrid video. All right, I'll see y'all tomorrow, 9 o'clock. Bring a calculator, 4 note cards, do the eval. See ya.
Hey, I have a quick question really quick.
Yeah, Abby.
I think you talked about this before class started. Did you say that you were gonna fix the grades, like drop the lowest ones, or is that already added?
No, none of that's been done yet. All the grading, I've got to, that's what I'm about to do today and
Okay, that's
into
what I
tomorrow. Yeah, so
Yeah.
by the end of the day tomorrow, you should see what it will look like.
Okay, sweet. Thank you.
Well, all the grades we put in tonight, yeah, Cameron, so I'm about to sit down and grade your remaining labs, homeworks and all that. Those should be in by this afternoon. And obviously the final exam grid won't be in until tomorrow and the Flipgrid stuff. So, but the other things should be in. All right, see ya. You're welcome. Have a good one.